Alright, so in this video I'm going to be taking a look specifically at progressive waves and later get onto superposition of progressive waves. And in the next video following this I'm going to move that on to look at how we make stationary waves. So let's get started straight away. So first thing, what is a progressive wave? Well, it's a type of wave that transmits energy from one place to another. That's the very essence of it, and most waves are a progressive type waves because like light waves take energy from a source which has very high energy like a star to elsewhere, and then any other waves like water waves take energy from high to low. Essentially it's anything that moves energy from one place to another in the form of oscillation. Okay, so that's what we've got here. So the energy will always go from somewhere that is high energy to low energy. I mean, that's a universal law actually. Energy always does go from high energy to low energy. And we also can break progressive waves down into two types. So there's longitudinal type waves and there's transverse type waves. And I'm going to dig into a little bit more what these waves look like now. First off, let's have a look at longitudinal waves. So what a key feature when you're looking at longitudinal waves is you'll see these regions of compression and what's called rarefaction, so where it's spread out and stretched essentially. So those are the characteristics of when you're looking at a longitudinal type wave. Sound is the most common example of longitudinal waves, although some seismic waves can be longitudinal as well. So essentially what you find is that the particles of the medium a longitudinal wave go through oscillate parallel to the direction. So this is transmitting energy from left to right, and the particles of whatever medium it's travelling in, be it air or solid or whatever, will be going backwards and forwards parallel to that direction. That's a longitudinal wave, and that's what's happening when a sound wave passes through things. Okay, so here we have an example of a sound wave. So what we've got here is we can see that essentially this is pulsing backwards and forth, sending a wave along this way. If we focus in on the individual particles like this one, you see it doesn't have any net movement. It's just oscillating backwards and forwards, from left to right essentially, as the wave passes through, which is a characteristic of a longitudinal wave. Alright, so that was longitudinal waves. Let's now talk about transverse waves. So longitudinal is when the particles of the medium oscillate parallel to the direction of energy transmission. Transverse is when the particles will oscillate perpendicular to the direction of energy transmission. So in here we've got the energy being transmitted from left to right, so the particles of the medium will oscillate up and down. And this is the form of a wave people are most familiar with, looking like this one here. So that's a transverse wave. Some examples being electromagnetic waves, so light, UV, radio, whatever, they're all transverse. Water waves that you see in the sea, those are transverse. If you have some string and go like this with it, that's going to make a transverse wave as well. So there's lots of examples of those. So let's dig a little bit more into those. So if we play the animation like I did before, so we've got the wave we can see coming from left to right. If we focus in on this particle right here, we can see that it is just going up and down. It's not going left to right the way the energy is transmitted. It's just going up and down perpendicular to the energy transmission. So we can see that we've got a transverse wave going on here, and we can see the particles of the medium don't actually move from like here to here, they just go up and down. So let's look at a few features of a wave. So regardless of what type of wave it is, longitudinal or transverse, we can represent it as a waveform. So transverse waves, that's easy because they look like this anyway. With a longitudinal wave, what we do is we represent a compression as a maximum and a rarefaction as a minimum. So again, we can represent it in waveform, which makes it easier to analyse and look at. So there's a few key features of a waveform. So we've got wavelength here, which is essentially the distance between the same point on a wave, usually between maxima or between minima, because they're easiest to find. We've got the amplitude, which is the maximum displacement from the equilibrium position, which is shown by this black line. This is the point the particles oscillate about, so up and down here. And so the amplitude is the distance between the maximum and the equilibrium, or even between a minimum and equilibrium. They're both the same value there. So those are those. let's have a look at a few properties of waves. So the first property of a wave I'm going to talk about is the frequency, which is defined as the number of full waves per second that pass through a fixed point. So what do I mean by full wave? So if we go back to look at this, a full wave is essentially where it goes through a complete cycle and reaches the same place again. So this is one full wave. So frequency is how many of those per second pass through a point. Okay, links to frequency is something called time period, which is the time it takes for one full wave to pass through a fixed point. And you have this inversely proportional relationship between frequency and time period, and the constant of proportionality is actually 1 in this case. So frequency is the reciprocal of time period. So if you know frequency, you know time period, or vice versa. So frequency is measured in a unit called hertz. But we can see from this equation that a hertz is equivalent to 1 over seconds, or s to the minus 1, which will be useful in a second. So that's our first two properties, frequency and time period. The next one we're going to look at is speed, which is essentially how fast energy is transferred through, so the distance the energy moves per second for the wave. So we can essentially see how far an amplitude moves in a certain unit of time to do that. And we get this equation to relate these properties of a wave. So it's called the wave equation, so speed is frequency times wavelength. So where does that come from? Well, we can see how it comes from by looking at the units. So frequency has a unit of hertz, which we've just seen is s to the minus 1. Wavelength is measured in meters. So we've got meters times seconds to the minus 1, so meters per second. So we can see that that gives us a speed there. The last property I'm going to talk about is the amplitude. So I'm not going to talk about too much, but essentially the amplitude gives you an idea of how much energy is being transferred by a wave. And actually the energy being transferred is directly proportional to the amplitude squared. So what does that mean? If you double the amplitude, it means it's transmitting 4 times the energy. But this one will become much more important when you get into the simple harmonic motion and oscillation part of the course. This is very useful, but it's important to stick it in now so you know what amplitude signifies. Okay, so we've talked about the impact on the medium of one wave passing through, but what if multiple waves pass through the same medium? What happens then? Well, we get this phenomenon called superposition, where essentially the amplitude of the two waves passing through will add together. So we're going to look at a few different scenarios to see the outcome of it. So the first thing we're going to look at, where we have two waves with the same wavelength that are in phase with each other, which means they're at the same point in their cycle at the same moment in time. So we can see here, these two are both at their maximum at the same time and their minimum at the same time. So what happens there is the two peaks add together to give you a bigger peak, the two minima add together to give you a bigger minima, so we get a bigger wave, or what's sometimes called a super wave, or super peak and super trough formed there. That's if they're in phase and have the same wavelength. Okay? So that's that one. So what if they're the same wavelength, but they're in what's called anti-phase, where when one's at a minimum, the other's at a maximum. When one's at a maximum, the other one's at the minimum. Well, because these two aren't the same size as each other, what's going to happen is they're going to cancel each other out, because one's negative when the other one's positive. So you get a smaller amplitude as a result. Likewise over here, again, these two cancel out, giving you a smaller minimum. But what if these two had the same amplitude as each other? Wow! If they're in antiphase, still the same wavelength, but have the same amplitude, they're actually going to completely cancel each other out. This here is called destructive superposition, or completely destructive superposition, because we've been left with nothing as a result of the two waves adding together. This process back here is called constructive superposition, because putting them two together gives you a bigger amplitude overall. And it's these two phenomena that are going to be important when we look at stationary wave and how we construct stationary waves. So constructive and destructive superposition. Okay. So just to summarise what I've been talking about, so superposition means the amplitude of the waves will add together at all points, and when they're in phase, they will constructively superimpose, so they're going to get a bigger peak and a bigger minimum. When one's maximum and the other one's minimum, they'll cancel each other out, leaving you with a smaller amplitude and sometimes even zero amplitude. Okay, so that concludes this video on progressive waves. As I said earlier, in the next video I'm going to look at how we can use these principles of superposition of progressive waves to create something called stationary waves. So do check that out, but thank you very much for taking the time to watch this video. If you've spotted any mistakes or anything that's not clear from this video, please do let me know. I'll be more than happy to help out and try and fix it if there's something wrong. But thank you very much for watching.